Okay, let's move on with our crystal structures. So first of all, I would like to give you a brief overview over the crystal structures that we discussed thus far. You see here a table. You see here the respective formulas that we already looked at. So when we have the composition AB, then one possibility is that we fill all octahedral holes. If we do this in CCP, then we arrive at the sodium chloride structure. And when we do this in HCP, then we arrive at the nickel arsenide structure. The other possibility to realize the composition AB is to fill 50% of the tetrahedral holes. If we do this in CCP, we arrive at the zinc blende structure, and when we do this in HCP, we will have the wurtzite structure. So when we have the composition A2B, then we can fill all tetrahedral holes. And in this case, we will have the calcium fluoride structure in the cubic close-packed lattice. The hexagonal analog is not known. We have discussed why. In the hexagonal close-packed structure, some of the tetrahedral holes are phase sharing and come very close. And for that reason, we cannot fill all the tetrahedral holes. So, of course, also the anti-fluoride structure is known. That would be also called the Li2O structure, in which then the lithium ions would fill the tetrahedral holes and the oxygen ions, they would make the lattice. All right, then we discussed we can realize the composition AB2 also when we fill half of the octahedral holes. And there are two possibilities. The first possibility is that we fill alternate layers of octahedral holes. In the cubic close-packed structure, we arrive at the calcium chloride structure. In the hexagonal structure is called the cadmium iodide structure. So if we fill half of the octahedral holes, not in a layered fashion, but isotropically throughout space, then we will get framework structures. In the cubic close-packed structure, that's the anatase. In the hexagonal close-packed structure, that's the rutile. We have learned that the rutile is slightly more stable than the anatase because in the rutile structure, there are only two edges that are shared, two TiO6 octahedra, or TiO6 octahedra, they share two edges with each other, while in the anatase structure, there are four edges shared, and that's not quite as favorable. So now I see that there are, of course, more possibilities. We could, for instance, also have a composition A3B, 3 cations, 1 anion, and one possibility to realize this structure would be to fill now all the octahedral holes and the tetrahedral holes. In the CCP, this is possible, and one compound that does that is the lithium bismuthide. In the hexagonal case, this is again not possible because we cannot fill all tetrahedral holes because of the phase sharing nature of some of the tetrahedral holes. All right, so another possibility is that for the composition AB3, we fill 1/3 of the octahedral holes. And this can be realized when we fill alternate layers of octahedral holes, but we do not fill them completely but only fill 2/3 of them. Yeah, so that is, for instance, realized in aluminum trichloride, in CCP, and in bismuth triiodide in HCP. All right. Also, other compositions can be explained with this concept. For instance, we can also have the composition A2B3. So when B are the spheres, then we can fill 2/3 of the octahedral holes in the 2/3 of the octahedral holes isotropically. And that is, for instance, realized in the hexagonal close-packed structure for the corundum structure. So alumina Al2O3 alpha alumina, corundum specifically adopts that structure. Okay, so this just is an overview and to show you the versatility of the concept of, well, hole filling in close-packed structures. The concept is even more powerful. You can also explain complex ions with this concept. So in this case, you would not have a single atom on a position of a sphere or position of a hole. You would have more complex entities. Okay. So here are just a few examples. So there are complex ion variants for sodium chloride. So for instance, pyrite, also known as fool's gold, the composition FeS2. So we've actually S2 to minus, S2 to minus anions. And you see that you see the unit cell of this crystal structure here. So you see that the iron atoms, they make the cubic close-packed structure. Sit on the face centers and the corners of the unit cell. And then the S2 to minus anions, they fill the octahedral holes. Okay, because they are sitting on the edge centers as well as the body center of the unit cell. Okay, but now the respective hole is not filled by a simple atom, but by a more complex building unit. All right, so a similar case here you have for strontium peroxide. So you see here again, strontium makes the cubic close-packed lattice, and again the peroxide ions, they sit on the centers of the edges as well as the body centers. They are sitting in the octahedral holes. All right, here just a third example. So the complex compound K2PtCl6 potassium hexachloroplatinate makes a CaF2 variant. So you see in this case that we have PtCl6 octahedra, PtCl6 2 minus octahedra, making the lattice in a cubic unit cell. You see here the corners are occupied by these octahedra as well as the face centers. And then all the potassium ions, okay, which are twice as many as the PtL6 2 minus octahedra, they sit here in the tetrahedral holes. All right, so now let us go from simple structures that we have discussed just now to more complex structures. And you will see that in these more complex structures, now not all sphere positions are being filled necessarily. And we do not only look at binary compounds, but we also look at ternary compounds in addition. So the first structure that I would like to discuss is the rhenium trioxide structure, ReO3. So the rhenium trioxide makes a primitive cubic unit cell, and in this primitive cubic unit cell, 1/4 of the spheres are occupied by rhenium, and 3/4 of the octahedral holes are being filled. So you see this unit cell here. So you see that there are these green rhenium atoms on the corner, in the corners of the unit cell, but there are no rhenium atoms in the face centers. All right. Therefore, overall, only 1/4 of the sphere positions are being filled. Okay. And now you see that the edges of the unit cell, they are filled by oxide ions, but the center, the body center of the unit cell does not contain an oxide ion. And you know that the body center of the unit cell also represents an octahedral hole. So that body center fully counts because we are on the interior of the unit cell. So therefore, one of the 4 octahedral holes is not occupied. So overall, we have 3/4 of the octahedral holes being filled. Okay. So overall, we have 1 rhenium trioxide per unit cell, the rhenium at 0, 0, 0, and 3 oxygens at 1/2, 0, 0, 0, 1/2, 0, and 0, 0, 1/2. Okay, so these fractional coordinates just represent the, well, edge centers. All right, so you have learned that in the cubic closed-packed structure, the sphere positions and the octahedral holes are commutative. Okay, therefore we can describe the unit cell also in a different view. We can also say that 3/4 of the CCP structure is filled with oxide ions, and then the rhenium ions fill 1/4 of the octahedral holes. So we can swap up the positions of spheres and octahedral holes and arrive at the identical structure because octahedral holes and spheres are commutative. Okay, so you see that this gives a pretty open structure. Okay, and what's interesting here is also that the oxygen is linearly coordinated by rheniums, which is a little bit unusual because, well, when we think of an oxide ion, we think of, well, an sp3 hybridized entity that is likes to be tetrahedrally coordinated, or when the coordination number is 2, we have 2 electron lone pairs that are sterically active. But that's not the case in the rhenium trioxide structure. Here we have a case where the oxygen is coordinated in a linear fashion. Okay, so as we can easily see, the rhenium ions, they are coordinated in an octahedral fashion by oxygen. Okay, so overall we have a 6-6-2 coordination. The rhenium has the coordination number 6, the oxygen has the coordination number 2. All right, then let's just continue with the next structure. So let's start this and then just switch the sharing. So the next structure that I would like to look at is the perovskite structure. The perovskite structure can be derived from the rhenium trioxide structure. The perovskite is calcium titanate, calcium TiO3. So this is the representative of our perovskite structure. And the titanium O3 partial structure is the same structure as the rhenium trioxide. Okay, so that means that we have titanium that make the lattice, but only, well, 1/4 of the sphere's sites are occupied by the titanium. And then the oxide ions, they occupy the octahedral holes, but not fully. Only 3/4 of the octahedral holes are being occupied. Okay, namely the oxide ions, they occupy the edge centers of the cubic unit cell. So now, however, you see we have a ternary structure. So in addition, we have calcium, and that calcium occupies, well, the remaining quarter of the octahedral site. So it sits actually in that body centered, in the body center here. All right. So what are the coordination polyhedra here? So like in the rhenium trioxide structure, the titanium is octahedrally coordinated by 6 oxygen atoms. So that calcium here in the middle of the unit cell is coordinated by 12 oxygen atoms in the form of a cube octahedron. Okay, so you see here actually multiple unit cells fused together, and you see here the cube octahedra with the calcium in the center and the oxygen at the corners. All right, so we can view the perovskite cell also again differently because of the commutative nature between the sphere sites and the octahedral holes. Okay, what we can do is that we can basically say that, well, our oxide ions and, well, our calcium plus, they make the spheres, okay, make the lattice. And then 1/4 of our tetrahedral holes are being filled with the titanium. So then we arrive at what is called the B cell of the perovskite structure. Now you see the sphere sites are occupied here with the calcium. So the calciums sit now on the corners of our unit cell. So that fills 1/4 of the sphere positions. So the other 3/4 are now occupied by oxygen. Okay, and you see the oxygen sit now in the phase centers of the unit cell. So now 1/4 of the octahedral holes must be occupied by calcium, and that octahedral hole which is filled is the one in the body center. Okay, the one at the edge centers here, they are not being filled. So that perspective shows you more clearly the octahedral coordination of the titanium. You see that the titanium is here surrounded by 6 oxygen atoms in an octahedral fashion. So this A cell shows you a little bit better the cube octahedral environment of the calcium 2 plus. Okay, So the perovskite structure is a fairly tolerant structure. It occurs pretty often, partially because um, it forms even when the ions do not fit exactly into their holes. So the fairly large tolerance factor, which is expressed by the Goldschmidt tolerance factor, which says that, well, the tolerance factor T is the radius, the ionic radius of the species A in the AbO3 structure. So for calcium titanate, that would be CaTiO3, that would be A. So Ro is nothing else but the ionic radius of the oxygen, and Rb would be the ionic radius of the species B in CaTiO3, that would be the titanium. Okay, so now how do we arrive at this formula? We can arrive at this formula from geometric arguments. So you see again here the unit cell for the perovskite. So this distance here is the distance between the species B, that can be, for instance, titanium, and the oxygen. And this here is the distance between the, well, species A, for instance, calcium, and oxygen. Okay. Now here we have a 90-degree angle. So according to geometry, well, the radius A plus the radius of oxygen square is equal to 2 times the radius B plus the radius of oxygen square. So now when you take the square root of that, then this formula says that radius A plus radius O is, well, the square root of 2 times the radius B plus the radius O. Okay? So now that would represent the ideal perovskite structure, where basically any factor that I would put in front of the square root of 2 would be 1. Okay, or in other words, in this structure, both the titanium and the oxygen would touch, and the calcium and the oxygen spheres would touch. Okay, so that's the ideal case. However, this value for T does not necessarily need to be 1. The perovskite structure is fairly flexible. T can actually vary between 0.8 and 1.05. Okay, so now for T value smaller than 1, okay, the titanium actually doesn't fit. It's actually a little smaller than the octahedral hole in which it is placed, so it can actually wobble around, but still wobble around a little bit, but still the perovskite structure is stable. Okay, so the calcium titanate, which is called the peroxide, is actually not the ideal peroxide. So titanium does actually not fit perfectly into the octahedral environment, but actually this strontium derivative is the ideal perovskite, where the tolerance factor here is equal to 1. For the barium, then, the titanium is a little bit too small and it starts to wobble, as I mentioned before. This actually gives the rise of a property of barium titanate, which is ferroelectricity. So how can we understand this? So let's look at the barium titanate structure a little bit more closely. So because the titanium is a little bit too small, we actually have an ideal cubic unit cell only at a temperature of larger than 120 degrees. That is because at these fairly high temperatures, well, the activation barriers of for the titanium to move around randomly without any significant activation barrier is large enough, or is small enough. Okay, but if we actually go to lower temperatures, okay, then basically the titanium starts to stick toward, well, one face of the cubic unit cell. And then, of course, our cubic unit cell is no longer cubic. Okay? Okay, you see here the titanium is somewhat displaced in one direction toward this face of our cube. So now, because of that, this unit cell, which is now tetragonal because of the displacement of the titanium, is polarized. It has a dipole moment. Okay, the positive charge here is slightly moved to this end of the unit cell rather than to this end. Therefore, this unit cell has a dipole moment, which would point into this direction from up, downward. All right. So now the dipole moments within each unit cell, they feel each other. Okay. Therefore, you have actually a spontaneous polarization in your crystal. Okay. So this so you have an analogy to ferromagnetism, actually domains where these dipoles are being aligned. Okay, when you apply an external electric field, then you can align the dipole moments permanently in one direction. So when you remove that electric field, the polarization of your material macroscopically doesn't go away. Okay, and that gives rise to the property of ferroelectricity. Okay. Now, in addition to the regular cubic perovskite, we can also have hexagonal perovskite and so-called antiperovskites. Okay, so what is meant by hexagonal perovskite? An example for that is cesium nickel trichloride. So in this case, well, the anions in one of the cations, so in this example that would be chloride and cesium, they make the HCP lattice. Okay, and then 1/4 of the octahedral holes will be filled with nickel. Okay, we can also have an hexagonal antiperovskite. And anti means in this case that only the cations, they make the lattice, and then the anion fill the sphere. So in this example, we have cesium-3 So this is a hexagonal antiperovskite because the cesium and the gold cations, they make a hexagonal close-packed structure, and then 1/4 of the octahedral holes are being filled with oxygen. Okay, so the cesium-3 compound is actually an unusual compound in the sense that it's a suboxide with gold anions. So I've mentioned previously, I believe, that gold is actually the metal with the highest electronegativity, it has an electronegativity of about 2.4, which is very similar to the electronegativity of many non-metals, for instance, iodine or phosphorus are fairly similar. So when you analyze the structure of this compound, then you will find that you have bands of phase-sharing cesium 6O octahedra. Okay, that could be conceived as a cesium suboxide, CS3O, and in particular an oxidized version of it, CS3O+, whereby now the gold ions act as the counter ions of the cesium-3O+ sub structure. Okay, so this is a fairly unusual electronic situation that we have here. And it arises basically because of the extremely high electronegativity difference between the gold and cesium. So cesium is the most electropositive metal and the gold is the most electronegative metal. Okay, so we know hexagonal antiperovskite. We also know a cubic antiperovskite. So these are fairly common with ternary nitrides and carbides. So here's one example, magnesium 3 ASN. So because we talk about an antiperovskite, we mean that the magnesium and the arsenic, they make the close packed structure. So in this case, it's a cubic close packed structure. And then the nitrogen atoms, they occupy 1/4 of our octahedral holes. All right. So now let's go to an even more complicated structure. The lanthanum 2 CuO4 structure, lanthanum cuprate structure. So this structure can also be derived from the perovskite structure. And in fact, we actually have 3 perovskite type subcells that are fused together. So you see the 3 subcells here. There's actually 2 A cells here, and 1 B cell. So let us look at this B cell first. In this B cell, the oxygen atoms, they occupy the phase centers. So they make the spheres. And in addition to that, the lanthanums, they occupy the corners. So they also occupy sphere sites. And then the copper occupies 1/4 of the octahedral holes. In particular, it occupies the one in the body center. All right, so this is overall a B cell. And then this B cell is fused together with 2 A cells. You see in these A cells, now the copper sits at the corners, here and here. We have our oxygen here sitting on the edge centers, occupying 3/4 of the octahedral holes. And the last quarter of the octahedral holes are being filled by calcium. Now you see that there are these white balls here, and that means that these atoms are actually removed. Okay, rather than this phase here is occupied by these atoms, because that part of the unit cell here is fused with this unit cell here. Okay, and these 2 subunit cells, they share this phase here. Okay, so the same is true for the other A cell. Okay, in this case, the atoms from this phase are removed, and then basically these 2 subcells, they share this phase here, and this phase is occupied with, well, these 4 lanthanums and that one oxygen. So the combined cell then looks like this. Okay. So what's quite interesting about this structure is that derivatives of that structure was the first high temperature superconducting oxide, which was discovered in 1986 by Müller and Bednard, and these were awarded the Nobel Prize just 1 year later. And what they discovered was that a derivative of that structure, namely the lanthanum 2 minus X, strontium X, CuO4, has a critical temperature of 40 Kelvin. Okay, so we mean here by this structure that some of the lanthanums are substituted by strontiums. And the discovery that we have a record supercritical temperature of 40 Kelvin was considered extremely surprising, because usually oxidic compounds tend to be insulators or maybe semiconductors, but not metallic conductors. And here, great surprise, the highest so far observed supercritical temperature was discovered in oxide, in ceramic material. So that triggered a lot of other research. And shortly later, the first oxidic superconductor that conducted above the temperature of liquid nitrogen, 77 Kelvin, was discovered. And from that point on, of course, the superconductors became a lot more practical, because one can reach fairly easily the temperature of liquid nitrogen just by cooling nitrogen down to its condensation temperature. And we have a lot of nitrogen in the air, so it's pretty straightforward to do that. All right, so now let us look more closely at the respective material, which has the composition yttrium, barium-2, Cu3O7. Okay, so this structure can be considered to be a defect perovskite. Again, it can be conceived as a condensation of 3 perovskite substructures. Okay, so now 2 of them have barium in the center. Okay, and 1 of them has yttrium in the center. Okay, so you see here the fused cell, but now from the fused cell, some oxygen atoms are removed. Okay, you see them here with white dotted, indicated with white dotted lines. So these 2 are gone, these 2 are gone, these 2 are gone, and these 2 are gone. And the resulting crystal structure is then this one here. Okay. So therefore, this compound, yttrium, barium-2, Cu3O7, can be viewed as an oxygen-deficient perovskite. Okay? The ideal perovskite would have the composition of yttrium, barium-2, Cu3O9, but some oxygens are removed. Therefore, we have only 7 oxygens per formula unit. Okay. So now we have in this structure 2 types of coordination polyhedra for copper. We have vertex linked CuO4 squares. See actually the squares here. And you see that these squares are actually making bands in one direction, this direction here. And we have layers of CuO5 square pyramids. Okay, so these are actually these ones. Okay, so see here, we have a square, and then the fifth oxygen atom is being corner shared with these squares here. So in this case, we have a mixed valent compound. So we have partially copper 2 and we have partially copper 3. And it was found that the critical temperature is very dependent on the oxygen content. So for instance, when oxygen is 6.5, when we remove more oxygen, then we have still a critical temperature of 60 Kelvin. But if we go slightly below that, then our superconductivity breaks down. We have no longer a superconductor. And closer inspection reveals that when we remove more oxygen, then we actually remove oxygens from these corner sharing CuO4 squares. And it seems like this structural motive is very important for the superconductivity. So if we remove too many oxygen atoms from them, then our superconductivity breaks down. So this is an argument why likely the bands of the squares are responsible for superconductivity. Okay. So therefore, it is important that when you prepare this compound, that you prepare it in an O2 stream to ensure the maximum oxygen content, which should be as close to 7 as possible. Okay. So now you may ask, well, why can't I get more oxygen in there? For instance, why can't I make the ideal perovskite deuterium barium 2 Cu3O9? This is because then the average oxidation state of copper would be larger than 3. And that's just not possible because the oxygen doesn't have so much of oxidizing power to oxidize copper into an oxidation state of larger than 3 in the average. You can easily check that. So the oxide ions would have a charge of -2. Okay, so we have 9 of them. So we have -2 times 9. So that gives -18. Yeah. And so yttrium has a positive charge of 3, barium 2 plus 2. So we have 3 plus 2 plus 2, which gives 7. Okay. Now 18 minus 7 gives 11. And 11 over these 3 copper atoms, that gives something which is larger than 3. Okay. Therefore, this composition is actually not possible. We can only get as many as 7 oxygen into that structure. All right. So after that discovery, there was, of course, a lot more research going on, and people believed that with a little bit more development, soon we would arrive at a room temperature superconductor. But after a few years, actually, that field halted. So you see that very quickly it was possible to go from 77 to about 100 to about 20, 140, and even 160 Kelvin. But that was all achieved in the early 1990s. And since then, actually, the field has not really yielded any better materials. In that record holding material is actually a high pressure phase. So only at very high pressure, that phase is stable and becomes superconductive. However, there have been some more recent developments. So in 2015, it was discovered that H3S shows a superconductivity of 100 gigapascals in 190 kelvins. Okay, so this is a temperature of minus 83 degrees Celsius. So you can already reach such temperatures on planet Earth if you go to extremely cold places like Antarctica, for example, but still you would have to apply a 100 gigapascal of pressure in order to achieve superconductivity. So still we are practically far away from any real world application of a superconductor near room temperature. Okay, so how can you test for superconductivity? You can do this using an effect called the Meissner effect. So you do not actually have to measure conductivity. They're actually much simpler methods to probe for superconductivity, because a superconductor has the property of being an ideally diamagnetic material. And an ideal diamagnet repels magnetic field lines. It leads them actually around it. And therefore, when you place a magnet above a superconductor, that superconductor will float. Of course, that only happens below the critical temperature. Above the critical temperature, our superconductor will be an ordinary diamagnetic. The field lines can easily pass, and our magnet will stop to float. I actually found a video of that Meissner effect on YouTube, and I just wanted to show you that. Now I have to change my screen again. So let's share this screen. You can quickly watch this video here in the last All right. So I just got a comment you couldn't hear me while the video was playing. I guess you can hear me again now. So I was just commenting on the video. So as you could see that whenever there was liquid nitrogen present, well, the superconductor was below the critical temperature and the magnet floated. And whenever the temperature was above the critical temperature, when the liquid nitrogen evaporated, then superconductivity breaks down and then the magnet doesn't float anymore. So this is basically all that I commented. All right, then I think we can stop at this point.